here we go. I guess I should have gotten the point of the notes where I needed to be before we started. We're going to talk about colligative properties this morning. If I can find it. Here we go. Okay, and this is something that we didn't talk about last year. We didn't get this far. We were really, really close to getting this far, but we didn't, because the next thing that we would have covered in the solutions chapter would have been this. So, but it's not that bad. It's just going to be new. So that's the thing that makes it probably difficult. So when we talk about colligative properties, we're talking about certain things that will change based on will change the solution based on how much solute is dissolved in the solution. Okay, so there are certain things that change when we dissolve salt in water. There are certain things about the properties of water that then change. Okay, and so those are called the colligative properties. Now, it doesn't have to just be salt. Doesn't have to be NaCl. Anything you dissolve in water is going to change the properties of water a little bit, and really the reason they're called colligative properties is because it doesn't matter what you dissolve in the water. If something is dissolved in the water and it's an equal concentration to something else, so if we dissolve an equal concentration of sugar and salt ions in the water, then we're actually going to do the same thing to the water as far as lowering its vapor pressure and raising its boiling point and stuff like that. So that's why they're called colligative properties. So the ones that we're going to talk about are vapor pressure lowering, boiling point elevation, and they call it melting point depression. I've always seen it called freezing point depression, so we're going to call it freezing point depression. I don't know why they call it melting point, because if it's being depressed, you're freezing it, and it's just easier to think about freezing point. But anyway, and then osmotic pressure is the other one. Okay, so vapor pressure first. So you're just going to have to think about this. If we have water by itself, okay, water is kind of attracted to itself, right? And what's the main intermolecular force that water has? Hydrogen bonding, right? Okay, so water has a fairly high boiling point and a fairly low vapor pressure already, just because it has strong attractions for itself, so it's hard for those molecules to escape as a gas, okay? But you put salt into water, or some other solute that dissolves in it, now you've got something else in that water besides just water that the water is attracted to, okay? So now you've got this ion dipole thing going on here if you put an ionic compound into water. And now the water wants to leave even less. Does that kind of make sense? Because it's so attracted to the molecules or the particles that are now in it, okay? And so that makes it even harder for it to escape as a gas, and that lowers the vapor pressure of that water, or whatever liquid we're talking about, okay? So that's vapor pressure lowering. So we can say this is kind of a universal thing. Anytime you have a solute in a solvent, anytime you have something dissolved in water, it's going to lower the vapor pressure of the water, okay? Raoult's law is that the pressure of your solvent, okay, now this is going to be the solvent, is equal to the mole fraction of the solvent times the pressure that solvent would normally have at that temperature, okay? Now this is kind of an important thing to notice here, all right? I talked to you about this when we were talking about calculating mole fractions. You have to pay attention to whether you need to calculate the mole fraction for the solute or for the solvent, okay? In this particular equation right here, when we're doing this equation, this is going to be the solvent, okay? We want to find the vapor pressure of the water, not the vapor pressure of salt in the water, right? That wouldn't even make sense. So when we find the mole fraction here, we need to find the mole fraction of the solvent, okay? Water, whatever it is. Okay, so you got to just watch out for that. We'll have a problem coming up that we'll talk about that. Actually, it's right here. Told you it was coming up. There it is. All right, so we've got glycerin. It's a non-volatile, non-electrolyte. Interesting. Why do we need those pieces of information? Non-volatile, non-electrolyte. Well, first of all, what does volatile mean? probably be good to know that. Nobody on volatile? Okay, if I say a liquid is volatile, it means it evaporates quickly, okay? And so this glycerin right here is actually a liquid. So we're putting this into water, all right? So it's going to dissolve in the water, but the reason that they need to tell us it's non-volatile is because what would happen to the vapor pressure if the glycerin actually had a tendency to evaporate? That might actually raise the vapor pressure, right? Okay, so now it's no longer vapor pressure lowering, and so you need to know that this is non-volatile. Okay, it's not going to evaporate, and they'll usually say that when they give you a problem like this. Now the non-electrolyte part we'll get to in a couple minutes. Okay, I'm going to hold off on that, but they just need to tell you that, so just need to trust me for now. All right, they're giving us the density of the glycerin. We want to know the vapor pressure of the water, or of the solution. It's going to be water mixed with glycerin. When we add 50 milliliters of glycerin to 500 milliliters of water. Okay, and then they're giving us the vapor pressure of the pure water at 25 degrees. All right, so now we have to think about this formula that we have here. Okay, we want to find the new vapor pressure of our water after we add the glycerin into it, right? So how are we going to find the mole fraction here? Any ideas? Okay, we're probably going to use the density, right? So glycerin has a density of 1.26 grams per milliliter. And what is the density of water? Okay, 1. All right, so that's how we're going to get from milliliters to grams, and then we can get from grams to moles, right? So let's go ahead and change both of these. 50 milliliters of the glycerin. 1.26 grams in 1 milliliter. And let's just do this all in one step. And then we'll go from grams to moles. Glycerin, get my calculator here. I'm getting 92 for the molar mass of glycerin. Okay, so that's going to give us moles of glycerin, and then we got to do the same thing with the water. 500. This alignment's getting off here. The alignment's getting really off. Sorry. Hang on a second. Wow. Okay, sorry about that. So I kind of need to redo this real quick. 1.26. What did I say, 92? Okay. And then 500.0 milliliters of water. And this is 1 gram in 1 milliliter. And there's about 18 grams in 1 mole of water. Okay. So then when we calculate both of those things, this is going to give us about 0.6, what are sig figs here? I guess 685 moles of the glycerin. And 27.8 moles of water. Okay, so now what? We know the moles of each thing. Okay, now we need to find the mole fraction of... Okay, and again, here's where you have to be careful, right? We need to find the mole fraction of the water. Now, I didn't label either of these. I should probably do that. This is a C3H8O3, and this is the H2O. Okay, so to find the mole fraction of the water, just do that up here. That's going to be 27.8 moles divided by You have to add that to the 0.685. I'm getting 28.5. And that's going to give us the mole fraction. About 0.975. Okay? So then once we have that, then we can just, plug it into our formula. So our pressure of the H2O, the new pressure, is going to be our mole fraction, which is 0.975, times the original pressure, which is 23.8 torr. Now, they're not specifying which unit they want the pressure in. Okay, and this 0.975, remember, mole fraction is a unitless number because moles cancels out. So we can use any unit of pressure with the mole fraction that we want to. So since they gave us torr, let's just use torr. So then we take the 0.975 times 23.8, and that gives us a vapor pressure of 23.2. Okay. So the new pressure of the H2O is about 23.2 torr. Okay, not a huge difference, right? I mean, it's still a fairly significant. I mean, it's still very close to the same vapor pressure, but it did lower a little bit because of the substance that we dissolved in the water. Okay, so that's vapor pressure lowering. Does that make sense? Any questions about that? Okay. All right. Next thing, well, okay. Before we go on to the next thing, we need to talk a little bit about real versus ideal solutions. This is kind of like real versus ideal gases. All right. We simplify these things a little bit when we're first teaching them to you so that you don't have to do really complicated math along with these. But we're going to make a couple assumptions when we're dealing with these things. We're going to assume for all of these types of problems that we're doing today that we have ideal solutions. And an ideal solution is similar to a real solution when the solute and the solvent are similar in size and when they have similar intermolecular attractions. Okay, now if we go back to this last one here, glycerin C3H8O3, that's not exactly the way this thing, I mean, this doesn't tell you a lot about the structure, but there actually is some hydrogen bonding in glycerin, okay? So you got hydrogen bonding in glycerin, hydrogen bonding in water, so in that sense it's ideal. But the size of these two is a little bit different, right? Okay, so not entirely an ideal solution, but we're going to assume ideal for most of these problems, for all of these problems that we're doing. Okay, and anytime you see a problem like this on the AP exam, it's probably going to tell you, assume that you have an ideal solution. I've never seen one that doesn't say that. Okay, so you can kind of almost forget about that because we don't really talk about, like with gases, we talk a little bit about, okay, how would you calculate the volume of a real gas? What's the correction that you would do for pressure and the correction you do for volume? We don't do anything like that here. Okay, so you just assume it's ideal. Okay. All right. Now we need to talk about boiling point elevation and freezing point depression. Okay, and hopefully this kind of makes sense too. Especially the boiling point elevation should make quite a bit of sense. If we are increasing the intermolecular attractions when we put something into water, does it make sense to you that it would take longer for it to boil? That kind of makes sense. I mean, think about the vapor pressure thing, right? If it's going to evaporate less quickly, then probably it's going to boil less quickly as well. Okay, so I'm sure that you guys have heard of putting salt in water for cooking, that sort of thing. That's actually a boiling point elevation thing. If you put salt into the water, it doesn't make the water boil faster. It actually requires the water to heat up more before it boils. Why is that good? Why is it better if we're boiling, if our water gets up to 105 or 110 degrees Celsius before it boils, as opposed to just 100? Then it will cook our food faster. You see how that works? Okay, so people always say, you put salt in water, it makes the water boil faster. Well, no, it makes your food cook faster because the water gets hotter before it boils. Does that make sense? Okay. What's that? Well, no, it's not exactly. That's different. And then freezing point depression. Same thing in the other direction. When you put a solute into water, actually, let me see if I have a little more explanation on this. No, I really don't. This just tells how to calculate it. Okay, so let me just go ahead and talk about this. So when you put a solute into water, remember, for something to freeze, those intermolecular attractions between the water molecules actually have to kind of solidify, right? They have to strengthen a little bit, or the molecules have to stop moving so quickly so that they can, sort of stay in place. If you have a solute in there, that kind of gets in the way of that freezing process. Okay? So you got something else that's in there, and it sort of blocks the water from being able to freeze and form its crystalline structure that it usually does. Okay? And so the water actually has to get colder before it can freeze. So it's kind of weird. It elevates the boiling temperature and it lowers the freezing temperature. Now, can you think of an example where freezing point depression is very useful? Yeah, I mean, we're coming up on that season, right, where they're going to start salting the roads before snowstorms, because as soon as that salt dissolves in the water that's falling, it's going to lower the freezing point of the water, and that means the water has to get colder before it freezes, okay? And that keeps it from, at least the hope is, that keeps the roads from icing up too much, okay? And so freezing point depression is actually another useful property that we can use to sort of make the roads safer during a snowstorm. Okay? All right, boiling point elevation. There's a formula for this. Let's see here. I believe all the formulas we're talking about today are on your equation sheet, with the exception of the osmotic pressure one. Let me double check myself and just make sure that I'm right on that. Not that it matters too much for the multiple choice, but the reason that matters is if something's not on the equation sheet, they're probably not going to even test you on it on the AP exam, most likely. Okay. Well, no, the osmotic pressure one is on there. Okay, so they're all on there. So I guess it's good we're covering all of them. So this is a fairly simple formula. If you want to know the change in the boiling point temperature, now this is the change in the boiling point temperature, so we have to do something after we find this delta T. We'll talk about that in a minute. There's a boiling constant for each given solute, okay? And then there's a little m here, stands for molality, not mass. So you have to be careful with that, okay? You guys remember what molality is? Close. Moles divided by liters is molarity. Moles divided by kilograms, right? It's moles of the solute divided by kilograms of the solvent. So we've got to use that in order to find this boiling point elevation here, okay? And then when you find the delta T, you have to add that to the normal boiling point, all right? And so you've got kind of one additional step. After you find this, then you add that to the normal boiling point right here, and that'll give you the new boiling point, okay? So the boiling point elevation might just be, you might get like 2 degrees here, okay? If you put that for your answer, boiling point of water is now 2 degrees. Well, that's not quite right, right? It would be 102 degrees. You have to add that to the normal 100, okay? All right, so change in freezing point it's a very similar equation here. It's just you've got a K constant, freezing constant instead of a boiling constant, but it's basically the same thing. And here you have to make sure that you subtract whatever temperature you get here. You have to subtract that from the normal freezing point. Okay, so if you get a delta T there of 2 degrees Celsius, then the new freezing point of water is going to be negative 2 degrees Celsius. Okay, that's how that works. And again, this is why it's a colligative property. It doesn't matter what the solute is. All that matters is how much of it is dissolved. We want to know how many moles of the solute that we have, okay, in a certain amount of the solvent. Okay, so let's try this one. Automotive antifreeze. Now this is another really useful application of freezing point depression, is the antifreeze that's in your car. Okay, you have something dissolved in the water, then your antifreeze is not going to freeze, antifreeze, right? And why is it bad if the water freezes as it's, moving through your engine? Yeah, well, for one thing, I mean, that water needs to be moving to help lubricate everything in the car, right? To do everything it's supposed to do. But for another thing, anytime that water freezes inside a pipe, that's a bad thing because water expands when it freezes and then it can crack things and break things. And that's why you don't leave water in your hoses over the winter, that sort of thing, or in your sprinkler system if you have one of those. Okay? So this is a really important concept here. So you've got this antifreeze, which is ethylene glycol mixed with water, okay? And it's a 25.0 mass percent solution, okay? And we want to know the boiling point and the freezing point here, all right? So in order to do that, the first thing we're going to have to do is calculate the molality of the ethylene glycol in that solution, right? Remember, molality equals moles over kilograms. And this is moles of solute over kilograms of solvent. Okay? So, we have to think about this a little bit. We've got a 25.0 mass percent solution here. Any ideas how we would start this one? Okay, let's assume that we have 100 grams of the solution. Okay, and then we can sort of work from there. So if we have 100 grams of the solution, that means we've got 25.0 grams of the ethylene glycol, right? 25.0 grams of the C2H6O2. And we need moles of that. So let's just change that into moles. Let's see, it's going to be... Should have been able to do that one in my head, I think. 62 grams. It's going to give us about 0.403 moles of the ethylene glycol. Okay. Then we also need to know the kilograms of our solvent. Okay. So what's the mass of our solvent here? If we're assuming we have 100 grams solution, which we did, we need to stay consistent with that, 75 of those grams is going to be water, right? So then, I mean, some of you don't need to do dimensional analysis for this. Probably most of you don't. But 1,000 grams in a kilogram, so you divide by 1,000, that's going to give you 0.075 kilograms. Okay? So that's going to give us our molality. So we take 0.403 divided by 0.075. That gives us about 5.38 for our molality. Okay? And now all we have to do is just come back here and plug into both of these equations, and they're giving us this, the Kb and the Kf. All right, so this is actually, once you find the molality, this is pretty simple. So I guess I'll do this up here. Delta T boiling is going to equal. Now watch your units here. All right, this is in degrees Celsius per molal. That's kind of weird to say. So 0.51 degrees Celsius, and then times the 5.38 molal, and then these cancel, right? And that's going to give us a temperature. So then we should get 2.74 degrees Celsius. That's our boiling point elevation, okay? And they are asking for the new boiling point and freezing point, so we'll come back to that in a second. Let's go ahead and get our freezing point depression here. So delta TF is equal to 1.86 times 5.38 That gives us, am I doing that right? 9.999999. Okay, I didn't round quite like I had it up there, so yeah, about 10.0. Okay, so our new boiling point of water, assuming that our normal boiling point is 100 degrees Celsius, it's now going to be, yeah, they probably don't have sig figs on the chart over here, do they? 100.0, okay. Although that's kind of a defined quantity, isn't it? I mean, I think it kind of is. So anyway, we'll just go with the sig figs that we have here. So 102.74 degrees Celsius, that's going to be our new boiling point, okay? And then our new freezing point, I'm running out of room here, I'll write it down here, is going to be 110.0 degrees Celsius. Oh, I'm sorry, I did boiling point twice. Freezing point. Our new freezing point is going to be negative 10.0 degrees Celsius. Okay, because it starts out at 0 degrees Celsius. Yet another reason why it's good for people to be here. You guys can catch my mistakes. Yeah, that would have. You're right. Okay, so we have one more colligative property that we're going to talk about here, but before we do that, there's another little thing that they like to throw at you on the AP exam, because here's the thing you have to remember. Colligative properties do not depend on what it is, okay? It doesn't matter what the solute is. All that matters is how much of the solute is dissolved in the solvent, okay? Now, where that kind of comes into play a little bit is when you have ionic compounds. You remember earlier in the year we talked about when you put an ionic compound into water, it's going to split apart. And some things make more ions than other things, right? For example, like magnesium chloride, MgCl2, you're going to end up with 3 ions when it splits apart in water, as opposed to just NaCl, where you have 2 ions, okay? That actually makes a difference here, because MgCl2 splits apart into 3 ions. It's actually going to have stronger colligative properties than NaCl. If you have the same amounts of each that you initially put in. Does that make sense? Okay, so that has to do with how it splits apart in water. So what we need to do here is we need to think way back to when we were talking about strong electrolyte versus weak electrolyte versus non-electrolyte, because that comes into play here, all right? So this will be a nice review on that. So let's say we've got something like this, 0.10 molal in ACl solution. Molal. It's just weird to say molal. That doesn't sound right. So molal. I'll emphasize it. So that would be 0.10 molal in Na plus and 0.10 molal in Cl minus. So overall, when we put that into water and it splits apart, now we've got 0.20 molal. Does that make sense? It's the same thing we talked about earlier in the year. When you have 1 mole of NaCl, that splits apart into 1 mole of Na plus, 1 mole of Cl minus, and you have 2 moles of particles overall now, 2 moles of ions. Okay? Everybody with me on that? I know some of you struggled with this, when we talked about it earlier in the year, so now we get to come back to it. If you have a weak electrolyte here, for example, HF, okay, remember HF is a weak acid. Let's say that we have 0.10 molal HF. When we put that into water, some of that HF is going to dissociate and some of it will not, right? So the new concentration is actually going to be greater than 0.1 because some of those things split apart into ions, but it's going to be less than 0.2 because not all of them are going to split apart. Okay? Still with me? Okay. And then if we have a non-electrolyte, like sugar, okay, 0.1 means 0.1 because when you put that into water, it doesn't split apart into ions, it just stays together. So you put 0.1 molal sucrose, it's just going to be 0.1 molal sucrose when you put it into water. Okay, so depending on whether it's an electrolyte or a non-electrolyte, that's going to affect how the colligative properties of water change based on it, okay? Okay, so let's do a sample problem here, and this is very similar to one you might see on an AP exam, and I think there are a couple of these on your packet. List the following in order of their expected freezing points. So 0.050 molal CaCl2, 0.15 molal NaCl. Okay, it's got a big list here. So let's just go through these one at a time here. 0.050 molal CaCl2. Strong electrolyte, weak electrolyte, or non-electrolyte? You guys remember how to tell? Ionic compounds are always strong. Strong acids and strong bases are always strong. Okay? The only thing that's a weak electrolyte is a weak acid or a weak base. Alright, so what is this? CaCl2. It's an ionic compound, so it's a strong electrolyte, right? It's going to completely dissociate, completely split apart when you put it into water. Okay? So CaCl2 is strong, which means it's going to split apart into how many pieces? 3, right? 1 calcium and 2 chlorines, or 2 chlorides, I should say. Alright, so this is going to end up being 3 times the concentration when you put it into water. So it's going to be 0.15, is that right? So 0.15 molal in ions or particles or whatever you want to call it at that point, okay? Alright, next, 0.15 molal NaCl. Hopefully I have enough room to do all of these here. Strong or weak electrolyte? Or non-electrolyte? Okay, it's an ionic compound also, so it's strong. It's going to completely dissociate. But it's only going to split apart into 2 pieces, right? So we doubled the concentration here. So this ends up being 0.30 molal. Okay, next, 0.10 molal HCl. Strong or weak electrolyte? Okay, strong acid, so it's a strong electrolyte. And how many pieces is this going to split apart into? 2. So we're going to double our concentration here. 0.20 molal. 0.050. This is acetic acid. Strong electrolyte, weak electrolyte, or non-electrolyte? Acetic acid is not one of the 7 strong acids, which I'm sure you still all remember, right? Yeah. This is not one of these strong acids, okay? It's a weak acid. And so, because this is a weak electrolyte, we only can sort of give a range here, right? This is going to be, let's see, how do I want to say this? 0.050. It's going to be greater than that, but it's going to be, is that right? This is, no, I said that wrong, didn't I? I wrote that wrong. It needs to be like this. Gosh, what is wrong with this thing? Okay, but the concentration of the ions is going to be less than double this, right? So it's going to be less than 0.10 molal. It's somewhere in the middle of those two. Okay. And then the last one here, the C12H22O11. Strong electrolyte, weak electrolyte, or non-electrolyte? That's a non-electrolyte. That's a sugar, right? Covalent compound. So that's a non-electrolyte. So 0.1 equals 0.1. Okay, this doesn't split apart at all. All right, so then we list them in order of their expected freezing points. So which ones are going to have the, okay, in order, I guess it didn't really say whether to go highest to lowest or lowest to highest. So let's go lowest to highest, okay? What do we think would probably have the lowest freezing point out of anything on this list? I think the acetate. Okay, remember, it's freezing point depression, right? So the more solute we have, the lower the freezing point gets. Okay? So the one that's the highest concentration, that's the one that we would expect to be the lowest out of all the freezing points. That's the one we're going to have to get at the coldest before it will actually freeze. So the NaCl, that's going to be first, right? So then after the NaCl, what's the next lowest freezing point? The HCl. And then CaCl2. And then sugar, right? And then the last one would be the acetic acid, okay? Okay, does that make sense? You kind of have to be careful with that. Okay, osmosis, we're going to talk about this quickly. This is the one that you're probably least likely to see on the AP exam, but they did put the equation on there, so we'll talk about it. Some substances form semi-permeable membranes, and you guys learned about this in biology a while ago, or if you're in, anatomy and physiology now. Maybe you didn't. Anyway, you're supposed to. So what that means is the cell membrane basically lets some things pass through and not others, and it depends on the concentration inside and outside the cell. Okay? There you go. So most biological systems, or most semi-permeable membranes in biological systems, allow water to pass through, but a lot of the solutes are actually too big to get through. Okay? For other reasons, they're not able to get through because of the charge of the membrane or the polarity of the membrane. So in osmosis, you've got net movement of solvent from an area of higher concentration to an area of lower concentration. Okay, and so if you have, they've got an example here where you've got a concentrated solution on this side, a dilute solution on this side. Then the water is actually going to move from the dilute solution into the concentrated one. I know that seems strange, but the reason that happens is because the dilute solution actually contains a greater amount of water, okay? And so it's going to travel in this direction until it equalizes, okay? And you can actually see that the water molecules come through here. And the solute molecules would pass through the membrane, but they're too big in this example to get through, okay? So that's the idea with osmosis. The pressure required to stop osmosis is called osmotic pressure. Okay, and it's symbolized by this pi symbol here. Okay, and so the equation that you want to know is pi equals mRT. That's the main one. Now m here is molarity. Okay, in the gases it's molar mass, but here it's molarity. We're talking about solutions. It's moles per liter. Okay, so now we're back to molarity instead of molality. When the osmotic pressure is the same on both sides, then it's called an isotonic solution. That means that there's no net movement back and forth. There will still be movement back and forth, but it's in equilibrium at that point. Okay. So we call it hypertonic if the solute concentration outside the cell is greater than the concentration inside. Okay. And this is why you don't want to drink salt water if you're, really, really thirsty. And you're out in the middle of the ocean or something. So as you drink that salt water, you are taking in water that has a higher concentration of solute than your cells do. So then all the water in your cells is going to leave to try and equalize those concentrations. Okay? When the water inside your cells leave, that's not a good thing. Okay? That makes your cells hypertonic, and then you die. So don't do that, okay? They call it's the technical term for this is called crenation, which almost sounds like cremation. So you know, you're one step from death when your cells start to crenate. Okay. All right. Now the opposite can also happen. Okay. If you have a higher concentration of the solute inside the cell, then actually your cells can start to swell up. Okay. This is not good either. And there have been documented cases of people right before they run marathons who actually drink too much water. Or actually, they had this issue with fraternities a few years ago. I don't know if you remember hearing about that, where they were forcing their pledges to drink a ton of water. Okay? Not good, okay? Because that can actually kill you too. Either way that you go with this, it can be bad, all right? So that's hypotonic, and then you end up with hemolysis, which again just doesn't sound good. Right? Okay, so that's osmosis. Now real quick we need to talk about molar mass, and we may not have time to do a osmotic pressure problem. Maybe we can do that in class, but that one I'm not as concerned about. Okay. One thing that they may ask you is to determine the molar mass of a compound based on a colligative property. Okay, and here's how this might work. Let's say we've got a solution here, and it tells us what the boiling point of that solution is. Okay. So we've got our equation here, delta TB equals KB times the molality, right? Now in this problem, they're actually giving us this, and they're giving us the KB here, right? So we can use the molality here to find the molar mass of the solute that's dissolved in the water, assuming that there's only one, okay? So in this problem, again, it's a non-volatile, non-electrolyte, and the reason non-electrolyte is important is because that means it's not going to split apart or dissociate in water. Okay, so we've got 0.250 grams of the substance being dissolved in 40 grams of CCl4. Okay, so what we've got here, this is our change in boiling point. That's our delta TB, right? So 0.357 degrees Celsius is equal to our KB for the CCl is 5.02. And then we multiply that by the, well, what are the moles of the solute here? Yeah, we don't know that, right? Okay. That's kind of what we're solving for here. So what I'm going to do, I'm just going to say moles of solute over, now we do know the kilograms of the solvent here, right? What's our solvent in this case? It's the CCl4, right? And there's 40 grams of that. So we need to change that to kilograms. That's going to be 0.0400 kilograms. Okay? And then we should be able to solve this thing. Okay, so what we basically have here is, if I rewrite this a little bit, 0.357 is equal to 5.02 times moles over 0.0400. Okay, and so then we're just solving for moles. So we multiply both sides by the 0.04 and then divide both sides by the 5.02. That'll give us the number of moles of the solute that we have. And that should give us about 0.00284 moles of the solute. Okay. Now, the other thing that we know here is we know how many grams of the solute that we have. 0.250 grams. So what's molar mass? What's the formula for molar mass, or the units for molar mass? Yeah, it's mass over moles, right? Grams per mole. So if we know the grams of the solute, and we just figured out how many moles of the solute we have, just take grams divided by moles, that'll give us the molar mass. Okay? And so we've got 0.250 grams divided by 0.00284 moles And I'm getting a molar mass of 87.9 grams per mole. Okay, and so just by seeing how much the boiling point of the solution changed, we were actually able to figure out the molar mass of the solute that was in there. We're actually going to do a lab that's very similar to that on Thursday. Okay? All right, sorry, that one took a long time. But we'll do some more practice on that in class.